Hello, in this section we'll talk about the linear and shear strain rates. So if we take a fluid element in the xy plane, so this is the xy plane, and we take a fluid element of dimensions dx by dy, and if all the points of the fluid element have the same velocities u and v, so here we have points O, A, B, C. So if all the points have the same velocity u and v, then after a given time dt, the fluid element will be translated to another location. So if all points in the fluid element have the same velocity, then we will obtain a translational motion. So the fluid element will be translated from one location to another. So here we are sketching during an interval of time dt. So this is the new position. Of course it is exaggerated in order to show the new location of the fluid element. So there is no deformation, only translation from one location to another. However, if we have a velocity gradient, then the fluid element will deform. So we will have deformation of the fluid element. So we have two types of deformation, either a linear deformation, and it will be associated with the linear strain rate. So first we will talk about the linear deformation, and we will define the linear strain rate. So we'll take the fluid element in the xy plane. We'll draw the points O, A, B, C. So if at point O we have the velocity u and the same velocity at point A, and at the adjacent points B and C, the velocity u varies by an amount equal to del u over del x dx using Taylor approximation first order. So at points B and C we'll have the new velocity u plus del u over del x dx. So what will happen is that the segment AB will be stretched to a new length AB prime. So point B will be displaced to B prime, and point C will be stretched to C prime. So the strain rate in the x direction, called epsilon xx, is defined the linear strain rate in the x direction, is defined as 1 over dt into the change in the lengths of the segment AB, so AB prime minus AB, over the original lengths AB. So AB prime minus AB is just BB prime, the distance between B and B prime. So this distance is due to the velocity gradient term del u over del x dx. So we should multiply it by dt in order to obtain the distance BB prime. So the distance, of course, from A to B is dx, and from O to A is dy, the original lengths of AB and OA. So epsilon xx is 1 over dt into del u over del x dx dt over the original lengths dx. So dx and dt will cancel each other out from the numerator and denominator. So epsilon xx is equal to del u over del x. Similarly, in the y direction, we have epsilon yy is del v over del y, and in the z direction we'll have epsilon zz is equal to del w over del z. So now we will try to calculate the rate of change in volume per unit volume of the fluid element. So let's calculate the rate of change of volume of the fluid element per unit volume of the fluid element. So this will be equal to, so dV over dt, the rate of change of volume per unit volume, so 1 over v. So 1 over the volume of the fluid element is dx dy dz. The change in volume with respect to time, so the volume will change in the x direction and in the y direction and in the z direction. So in the x direction, this hatched region is the change in volume, which will be equal to the del u over del x dx dt, the multiplication of the sides bb prime into OA into the perpendicular distance into the paper, which is dz, into dy into dz. So this is the change in volume in the x direction. We add to the change in volume in the z, in the y direction, del v over del y dy dt dx dz, plus the change in volume in the z direction, plus del w over del z dz dt into dx dy over dt. So now we can remove dx dy dz dt from both the numerator and the denominator. So 1 over v dv over dt just equal to del u over del x plus del v over del y plus del w over del z. Del v over del y plus del w over del z. So in other words, it is equal to epsilon xx plus epsilon yy plus epsilon zz. Okay, the summation of the linear strain rates in the 3 directions. So for incompressible flow, of course we know that the density is constant and the variation in density is very negligible. And the density is equal to the mass over volume. Since the mass is constant due to the conservation of mass, then the fluid element should also conserve the same volume. So the volume of the fluid element should be also constant. So in this case, 1 over v dv over dt, there is no change in volume, should be equal to 0. That means that the summation of the linear strain rates epsilon xx plus epsilon yy plus epsilon zz should be equal to 0. This term 1 over v dv over dt is called the volumetric dilation rate. The volumetric dilation rate. So, for example, let's consider two-dimensional 2D incompressible flow, or an 2D incompressible fluid element. In this case, we will have that epsilon xx plus epsilon yy should be equal to 0. Then, if this is the original volume of the fluid element, if the fluid element is stretched from one side, for example here, so we have stretching in the plus or minus x directions, it should shrink in the y direction in order to maintain the same volume. So in order for V to be equal to a constant, so that the final volume in this case should be equal to the initial volume. So here the final volume or the initial volume in red, highlighted in red, should be equal to the initial volume highlighted in black. Now let's talk about another type of deformation. So deformation due to shear stress, and the shear stress will create a shear strain. So we'll talk about the shear strain rate. So if we have a fluid element in the xy plane, of course with the lengths equal to dx and dy, have the points O, A, B, C. So if at point O we have the velocity u, at point A, if this velocity is changed by an amount equal to del u over del x dx, so we'll have u plus del u over, del u over del y dy, so after a distance dy, and the velocity v from O to C will change by an amount equal to del v over del x dx. So point A will be displaced to point A prime, and point C will be will have a new location, let's call it C prime. So the segment OC will rotate to the location OC prime, and the segment OA will rotate to the location OA prime. So the shear strain rate is defined as half of the rate of decrease in the angle between two initially perpendicular lines. So the initially perpendicular lines are for here OA, which is perpendicular to OC. So half of the rate of the decrease in the angle, let's call it epsilon xy, the shear strain rate. So this angle is d alpha between OC and OC prime, and d beta is between OA and OA prime. So epsilon xy from the definition is equal to half into the decrease in the angle between the two perpendicular lines, which is the summation of the d alpha and d beta, of course divided by dt, since it is the rate of decrease. So the angle between OA prime and OC prime is decreasing at a rate equal to the rate of increase of the two angles d alpha and d beta, the summation of the rate of increase of d alpha plus d beta. So since d alpha is small, so tangent d alpha is equal to d alpha, and it is equal to del v over del x dx, the opposite side, into dt, since this is a distance, over the adjacent segment dx. So d alpha will be equal to del v over del x into dt. And similarly, tangent d beta is equal to d beta and is equal to AA prime. This distance is due to the velocity gradient del u over del y dy times dt in order to obtain the distance AA prime over the adjacent phase or the adjacent segment dy. So d beta will be equal to del u over del y dt. So then epsilon xy will be equal to half d alpha over dt is just del v over del x, and d beta over dt is just del u over del y. So we can repeat the same analysis to obtain epsilon xz. It will be equal to half into del u over del z plus del w over del x. Similarly, for epsilon yz, it will be equal to half into del v over del z plus del w over del y. So we can combine the linear strain terms with the shear strain terms in order to obtain a strain rate tensor. So we combine the linear and the shear strain rates in a second order symmetric tensor. So we'll call this tensor the strain rate tensor. We call it epsilon ij. So here we have epsilon xx, epsilon yx, epsilon zx, second column epsilon xy, epsilon yy, and epsilon zy. The third column we will have epsilon xz, epsilon yz, and epsilon zz. So as you can see, the diagonal of this strain tensor is the linear strain rate epsilon xx, epsilon yy, and epsilon zz. So let's write each term by its expression. So epsilon xx is del u over del x, epsilon xy is half del u over del y plus del v over del x, and epsilon xz is half del u over del z plus del w over del x. So epsilon yx is equal to epsilon xy. So epsilon yx is half del u over del y plus del v over del x. Epsilon yy is del v over del y, and epsilon yz is half del v over del z plus del w over del y. So epsilon zx is equal to epsilon xz, and it is equal to half into del u over del z plus del w over del x, and epsilon zy is equal to epsilon yz, which is equal to half into del v over del z plus del w over del y, and epsilon zz is equal to del w over del z. So this is the strain rate tensor.